Just a handful of details. One, I want to remind you, I've talked about this a few times now, let's say you didn't show proficiency with one of the skills earlier this year. What skills could this end up showing me proficiency with? What was involved in writing this equation? Write the equation of a line, right? So you were struggling with that earlier in the year. Keep in mind, hey, I can write the equation of a line. We're actually going to do it from tables in the next unit. So keep in mind, you're always going to have opportunities to improve your understanding of my class and develop it. But that means we need to make sure we're asking questions, okay? So I'm not going to say other names, but like I heard Miles pushing on his group really, really well, asking questions to make sure they truly understood, right? We don't get upset about people asking us questions to make sure we understand. If we don't fully understand, we need to make sure we're asking those questions, right, David? Because you got to be able to explain why. If you cannot explain why, I guarantee you the understanding of what to do will go away eventually. I think we've all seen this in the past where we take a test in a math class and we move on from that test and we basically forget what we did the previous day. Do you know why that happens? Because we don't actually understand why. We learned what to do, but not necessarily why to do it. We need to learn the why so that we can bring it back out later and we can use it and apply it later. So, in looking at this, I need to just quickly remind you, I love what Miles did here, is what I recommend. Notice, what is the first thing they marked on this graph here? Anyone know what it is? Or have a guess? The what? The zeros, right? Because remember, when we're dilating these functions, it's all about the what? It's all about those zeros. So notice they didn't just mark the zeros, they actually drew those vertical lines in here because that marks the different regions I want to look at for these functions. And they did a great job, this group, of noting, hey, all of these values, and when I say values, do I mean inputs or outputs? Outputs. All those outputs are negative. They're below the x-axis, they're negative y values, negative outputs, same thing here. And what do I get when I multiply a negative times a negative? Positive. And notice how I said multiply. I don't want you to ever forget this is all about dilating, right? The whole idea is that we are dilating these two functions. When I looked at v of x, what type of function was v of x? It was linear. What degree is a linear degree? I heard someone say it. 1. And it has how many zeros? 1, 0. But then I dilated it by another function, s of x, and that's also linear, so it's also degree 1, and it has 1, 0, and now all of a sudden my dilated function has how many zeros? 2. I need you to remember, what we're building is the set of functions known as polynomials, and when we dilate one function by another function, we are increasing the number of zeros. That's why we went from a degree 1 to now we have a degree 2. Like, that's the idea here, is that all these polynomial functions, the quadratics that you studied in the past, they have 2 zeros because it's a linear times a linear. That's some core idea, all right? In most ideas. Well, I'm going to talk about why that's not always true later this unit, or maybe it's next unit, I don't remember. It's 1 and 2. But keeping in mind, I'm dilating, I'm creating that new zero, and so a negative times a negative is positive, but it's decreasing because what does it have to get to? 0. It's got to get to that 0. It's all about the zeros. All right, so these are in between now, right? We've already done to the left. In between here, this linear has what type of values? And here it has, right? So these have negatives down here. What's a positive times a negative? So all of these are negative. Now, one thing I want to point out is I heard this discussion over in the kings and queens. They were talking about that vertex, right? Maybe trying to find what the vertex was. Now, first off, where do we always know all vertices are located? Like, what line is the vertex always on? Say it again. The line of symmetry, right? And notice, I know my line of symmetry. You don't have to do this, but I'm just pointing out you can do this. And so my vertex is here on this line of symmetry, and notice, what's the output right here? It's 1. What's the output right here for s of x? And what's 1 times negative 1? So the vertex for this parabola would be at negative 1, negative 1. You don't have to do that because we've just been focusing on positives and negatives, but I do want to point out that you can get more specific and actually look at individual y values, right? You could look here. What's this y value? This one right here. Negative, that's x. The y value, negative 1. Can you hit the lights for me real quick, Drake, just so it's a little bit easier to see? So that's negative 1. What are these y values, or what's this y value? Negative 3. And what's negative 1 times negative 3? Positive 3. We're multiplying the y values. If I wanted to get more precise, that's what I could do. We're just focused on positives or negatives, but notice, you can get more precise with those individual values if you want, right? Maybe that's something I add into the exceeds in the future, like creating a precise graph, not just sketching based off of those y values. It's not there yet, but if you want to do that in the future and get more precise, I might add that in. Right? Notice here, 1 times 3 is 3. And so I can get a more precise graph out of this, but we're just focused on the positives, the negatives, and the zeros. Okay? And so, these are positive, it has to decrease to get to 0. Then it goes into the negatives. Why does it turn around at the vertex? It's got to get back what? To that 0, right? It's all about the 0. So it's got to turn around somewhere and get back to the 0. And then what does it continue to do? Go up. What? Do you know what the mathematical term for go up is? Increase, right? There's decrease and then there's increase. We're going to play with that decrease and increase a whole lot more next unit. What questions do you have about just graphing? I want to make sure all those things are clear. I know I spent a lot of time, more time than I planned on it, but I think there's important discussion bits there. Looks like we're making sense out of it. Okay. For the equation side of it, I just want to emphasize and point this out. P of x is literally taking s of x and dilating or multiplying by v of x. So if you can get an equation for s of x, if you can get an equation for v of x, that's it. The equation for s of x, these are linear functions, right? Is this one s? Yeah. What's the slope? Up 1 to the right 1. What's that slope then? 1x. What's my y-intercept? 0 plus 0 times v of x. What's my slope? Up 1 to the right 1, so the slope is 1x. What's my y-intercept? 2. That's it. Now, you can simplify. You didn't have to write it with this level of detail. 1 times x is just what? X. X plus 0 is just x. So a lot of us wrote that. Perfectly acceptable. I would 100% accept either of these equations. Especially if you show evidence for getting there. Make sure you show the evidence of the slope and the y-intercept. What questions do you need to ask? Go for it.
So would that equation would that work too? That circuit equation?
Say it one more time.
Would that factor equation work too?
Yeah, you can leave it at that factor equation. If you want to get the standard, sure. But what did I ask for? I just asked for an equation. So you could have distributed and gotten the standard, but did I ask specifically for the standard equation? So could you have left it at factored? Yeah. Now if I ask for standard, go to standard. But if I just say an equation will do. In fact, this group over here started trying to do the vertex form, and it's 100% valid. If you find your vertex, you can do the vertex form. I just made the suggestion, hey, we already have 2 linear factors, go with factored form. So you could, just need an equation. Now, we'll make this note. When we get into cubics, you know what the easiest form to start with is? Oh, I'm going to come back to it in a second. I will point out, if I say a cubic, does a cubic function have a vertex? Remember, we've been looking a little bit at these cubics. They look something like this, maybe. Right? There's no vertex there. So, we're not going to go with the vertex form. You could do standard form, but remember, these cubics are being created by linear what? Functions, which can also be called, there's another F word. Remember, these lines are the factors for that cubic function. So you know what form I would start with? Personally, I would start with factored form. That's going to be the easiest to start with. This whole unit is the idea of dilating to create new functions. So I would start with factored form. Alright, I want to give you a little bit of time to update any notes you need to off of the discussion. I'm going to look at the Ferrer models really quickly. That's the wrong one. There we go. This might be good Maybe updating some notes on transforming the function shapes, if you needed some help there. Maybe on predicting the shape, if you needed some help there. Not multiplicity in standard form. So, if you need to update any notes on either transforming the shape, look at it. And remember, the transforming the shape is the idea of dilating, multiplying those outputs. You need to update any notes there, go for it. If you want to just write notes on that page from the textbook, you can. One thing I'll make a note of really quickly is that we have, you'll see admin and teachers walking around today for instructional rounds. So they don't want to see assessments today. I forgot about that. So they're more focused on seeing teaching and learning. So we're going to do our demonstrating understanding on all this stuff tomorrow. Okay? So I figured today would be some good practice, and we'll add in something new that won't be on the demonstrating understanding. But I figure that gives some of us who need to ask some questions and learn time to ask questions. Not look at anybody in particular. Nah. Alright, come on. Do your notes, update your knowledge, add whatever you need to, ask the questions that you want to during this time. We're going to come back together in just a few minutes to move our understanding forward. What? Yeah, students have been tearing up my 4s or losing them.
Last week, math is equal.
You ate one of my cards? Come on, hey, you need to update some knowledge. Update your notes to your future forgetful self. Talk about anything you need to improve your understanding. If you heard something like, ooh, I should write that down, let me know. I will make the note, we're going to use the next activity or the next page in the textbook if you want to get that page out afterwards. If you want to do some practice problems during this time, you can. I'm going to turn up the temperature a little bit. Huh? Yes, that sounds right. I have a little bit of toilet paper left. I'll get some more, but there's some up there. If there's not enough, then you can go through about that. Yeah, page 173 is what we're about to use. So if you do finish your notes to your future forgetful self and want to start working on the question on 173, then you can do that. What's November?
I said she needed to write some notes because she's still talking about concavity, and we did concavity like 3 minutes.
I knew I was thinking about it at first, and now it's confusing
Hey,
when you kept
slow
saying
down.
no.
Listen, concavity is important, and we do want to talk about concavity. We just need to remember when we're dilating functions, we're focused on the idea of multiplying those two factors, multiplying the outputs. Now, I will point out, something to consider is, when you look at that factored form, you have a positive slope times a positive slope, right? What's a positive times a positive? So that A is going to be positive, which is why it's concave up. So concavity does matter. But I will point out, when we start looking at those cubics, right here, when we move into the cubics, there's not just one concavity. This concavity would be what? Well, concavity is up, but then it transitions into concave down. So when we talk about functions higher than quadratics, higher degree, you're going to have more than one concavity. Remember we talked about that point of inflection with normal distributions? It's that same idea. You learn more about that in a calculus class, but that's not a focus for
That's
us.
what we got new here.
No,
You don't have to.
you don't have to take
I'll
calculus.
take
What we got to
statistics.
take?
You can take pre-calculus statistics. I'm gonna try to get a data science course started. I don't know if if that'll happen.
Which
And
one
then,
happened?
huh?
Which one happened?
Calculus.
I mean, I don't know about all that. I love AP statistics because it's a lot of real-world application, but it's an AP class. If we do a data science class, there's a lot of statistics involved with it, but it's also learning how to use computers to gather and analyze data, and it's not as rigorous as an AP course.
That's usually fun.
Sorry,
Back in the same.
I'm glad you got it though.
AP stats? Yeah,
Huh?
that's good. It's gonna take at least one AP class.
Oh,
Yeah, the idea is of multiplying the outputs, and so we focus on positives and negatives, but one, we can also just focus on the individual values, one times negative one is negative one. So the vertex would be -1, -1. Good question. All right, any other questions?
nothing like it.
1, 2, or 3, how many more minutes do you need for notes? Okay, looks like the majority of us then are done. Did you have a question? Or you just stretching? Oh, my bad, okay. So Demi, go ahead and finish taking your notes. For the rest of us, then, since we're already done, I just want to quickly note, we are doing the corresponding textbook pages. We're going to take about 10 minutes to do this, just the very next problem, because I really want to get into the painted cubes task. It's one of my favorite ones that we do. So, it's to help us understand cubics a little better. So, let's move on to page 173. Oh, and don't forget your focus. What we are focusing on right now is still sketching polynomials when given the graphs of the factors. That's the priority at this point. And determining if the y values of a polynomial are positive, 0, negative, based on the graphs of the factors. Not doing that this time. Ish. Alright, so this page 173. What I want you to focus on here is I just want you to sketch the function for v of x. So this is based on something earlier in the textbook that we ended up not using, but I want you to find the equation for v, or the graph for v of x, and let's say this, let's find the standard form for v of x.
So would this
We got calculators though, right?
Oh, but if we're writing. Oh, you're saying those.
Yeah, if we're writing it in standard.
No, you didn't, Brandon.
Same thing as
I
with
think it's
different
6
lines, right?
x squared
Same slope.
plus. I'm gonna go ahead and just do 4x squared
All three of those.
minus
Oh, that
60x
was.
plus 260. And then what would I need to do with this? That's it though. We just distribute that you want.
Seriously, so confused.
Thank you. Thank you. Okay, if I can just grab y'all's attention really quickly, we're going to move on to painted cube in a second because I let this go a little bit longer than I intended. So what I want to point out is, and when you have these factors, right, please don't make it harder than it has to be. What's the first focus to be able to graph these factors, or graph the dilated function? What do we got to identify first? Zeros, right? Like the focal point is those zeros, and then whether the function is positive or negative after that, right? And so we can get more precise, 100%. But it's just this idea that if I'm looking to the left of my 0 here, all of these values are what? Positive. Shadidra, you with me? Focus over here real quick. Miles, don't stress it. Okay, all of these are positive. Why are these positive? They're above, what did you say, Shadidra? The x-axis, right? They're above the x-axis. Those are all positive values. You can literally look to the right and like, oh, those are positive. All of these are positive, and all of these are. If I take a positive times a negative, I get a. Yeah, I'm gonna. No, yeah, I'm about to go over there in a second. So just hold on. So all these values are negative, and it's got to get up to that 0, right? So negative values into the 0. Now I look in between my zeros. Okay, that's it. And I got positives, I got positives, I got positives, and when I multiply through positives, all those outputs are positive, right? So, but I got to get back to the, and Davis is doing a great job talking about this of, hey, it's got to turn around, right? It's got to turn around and go back down. It's got to start to decrease. And so I was pointing this out to Shadidra, and I want us to note this. Actually, let me talk about it over here really quickly. Shadidra was very heavily talking about concavity with those quadratics, right? But with these, what type of function is this again? What type of function would we have here? Cubic, right? X cubed. How do we know this is going to be cubic? 3 roots, right? 1, 2, 3 zeros. When we talk about these cubics, is there just one concavity in there? Because look at this region. What would I call this section right here? Concave down. What would I call this section right here? So quadratics are the only place that we only have one concavity, okay? Or at least so far. I think we actually saw that with exponentials as well. But my focus is with these polynomials, only quadratics have one concavity. Now, one thing I want to caution is, overall, this is a pretty good sketch. I would have one slight issue with this sketch. Does anyone know why?
No.
None at all? Drake, what are you thinking?
The color coding is kind of.
Color coding I'm fine with. Like, here's the thing. If you want to color code, awesome. I love the color coding, but you don't have to have that. What? Can you come circle it? What are you thinking it is? Yep. Okay. And more than just this right here, I would say all of this. So that's good thinking. Why do you think? And so like this is a great sketch overall, but why do you think I might want to push back on the way that that section is sketched? At some point it looks like a straight line, or it almost looks like it's going back in. What would this not be though if we have a straight section or it even curves back in? What would it not be? Something even more important. It's not a function. So here's the thing. It's a sketch. I get that. But when you do your sketches, make sure you go back and you look and say, is this drawn like a function? The way I'm seeing it right here, it almost goes out and then it comes back in a little bit. So if I draw a vertical line, how many times does that vertical line hit that function? At least twice. So one input has more than one output. So it wouldn't be a function. We need to be careful about that detail. Does that make sense? Okay. So again, it's a great learning opportunity. Don't stress it. Learn from it. It's okay. The last thing I want to talk about before we do my favorite painted cube, man, I hope we have enough time for this, is over here, if you look at the area model, or I asked y'all to go to standard form. Again, I noted that the textbook had a really odd writing of that equation. Hey, come on in. But I'm just using the one that the book wrote. It wasn't 100% right. How did we go from our factored form to our standard form? What's that key idea there? The area model. What does that area model help me do though? So remember, the area model is just a model. Xander has a completely different way of doing it that is 100% right. What does that area model help me do though? Distribute, right? So Xander just distributes without the area model. Is that 100% okay? Yes, 100%, right? You can 100% do that without the area model. Just remember that area model helps me distribute. Okay? And so if I want to go from factored to standard form, use that area model, distribute it out. Do remember though, because this is one of the things that caught a lot of us on this test, once you distribute this, are you done? No, we got a whole nother factor right here. Does that make sense? Be careful about that. All right. So again, that was just a little bit of practice with those skills. Now we're going to get into that painted cube task. So go ahead and rejoin your groups for me really quickly while I describe and lay out the situation of the painted cube. Or you can just stand there, Kyron. That's cool. You're good, dude. I'm just messing with you. All right. Okay. We'll get some more practice, I think, maybe with this. Yeah, we'll do a couple of these before the demonstrated understanding tomorrow. But this is the fun thing. So, what we are looking at, if you're looking at your proficiency scales for this unit, the main focus right now is this. What type of function did we start sketching here? We said it earlier. It was what? Cubic, right? We got a cubic function. Elizabeth, you pointed out we knew it was cubic because of what? There's 3 roots, right? We got 3 roots in there. It's got to be a cubic function. But let me ask you this. What is a cubic function? A function with 3 roots, but there's got to be more to it than just that, right? When we study quadratics, what all did we learn about quadratics? It had a what? It was a linear times a linear, okay? So if we took a linear function, multiplied by a linear function, we got a quadratic, okay? What else do we know about a quadratic? Let me ask you this. What do you know about a linear function? Okay, it's a line, but that's only telling me about the graphical representation.
Yes.
It's got a slope, okay? What else do we know about a linear function? It has an additive rate of change. Is it just an additive rate of change? It was what? It was a constant additive rate of change, okay? Hopefully that's starting to build us back up. What do we know about a quadratic function?
Constant additive, linear additive rate of change.
So linear additive rate of change, maybe? And so what is a cubic function? Like, what is the core nature of a cubic function, right? We're seeing that a cubic has that shape on a graph, right? We're seeing that a cubic has 3 roots. We're seeing that in the equation, Anyone get there? Not quite. Xander had it and I erased it, or someone else erased it. Really quickly, just pointing this out. When we look at a cubic, if I distribute this, what am I going to get? 4x cubed, or to what degree? Third degree, right? So we're seeing the algebraic nature. We've seen the graphical nature. What's the nature that we still need to look at? Tabular, right? We've got to look at those tabular representations. So we're about to talk about that rate of change pretty heavily. So here's the painted cube task. And I'm going to go ahead and set the stage with this. You will probably want to grab some of these in a few minutes. And so what we're doing is we're taking a cube. That's not the one. Those are not opened yet. So we're taking a cube, not just one cube. We're looking at multiple cubes. So a case 1 cube has how many cubes involved? Case 1 has how many cubes? 1 cube, okay? Got one little cube here. And what we're going to do with this one little cube is we are going to cover it in paint. Okay? Not physically, because they get real messy in the classroom. Okay, so hold on to that idea. So we're going to take 1 cube and we're going to cover it with paint. We got a case 4 cube here, and what do you notice about this case 4? It's what? 4 by 4? Is that it? Okay, I was just saying, come on, this is a cube, right? We've got how many dimensions with that cube? 3 dimensions, and say 4 by 4 by 4, okay? So what do you think a case 3 cube is going to look like? 3 by 3 by 3. So not a great job. I don't do a great job of drawing, so I'm not going to try drawing this. So this is why it might be useful to grab these pieces later. So notice I can build this cube out, right? That's not what I want. That's what I want. And so I'm almost there. One more. No, I'm not almost there. Sorry, I'm taking way too long on this. But it's going to be a what shape are we looking at here? A cube. So a 3 by 3. Once you build it out, we'll get there. So case 3 is a 3 by 3 by 3. And then what do you think a case 2 is going to be? Alright, so there we go. That would have been easier for me to create. Sorry, was being silly about it. So a 2 by 2 by 2. And what we want to do is we want to figure out, if I were to take these cubes and I were to pour paint on it, how many cubes have 3 painted faces? How many have 2 painted faces? How many have 1 painted face? And even have 0 painted faces. So, we want to create some mathematical representations. This physical thing can be a great help in thinking about this. But you can also see it right here. Does anyone see where you might have a cube with 3 painted faces, either here or here? Like if I pour paint on it, where would this have 3 painted faces? The corners, right? So 1, 2, 3. Okay. Where would there be 2 painted faces? Anything in the middle? So like here? This middle? So what could we call this? This would be the edges, right? So I want you to think about that, and I want you to build this out with your groups using this physical manipulative, or if you don't need it, don't create it. But I want you to think about how many cubes would have this many painted faces for a 7 by 7 by 7. Once you figure out a 7 by 7 by 7, I want you to extend that to a 15 by 15 by 15, and then an n by n by n. Now, the one hint I'm going to give you at this point is, what mathematical representation do you think is going to be most helpful in figuring out these pieces? Which one? That's an operation, but I'm talking about a mathematical representation. Crystal, give me one mathematical representation. Tabular, algebraic, graphical, verbal, and pictorial. This could almost be like pictorial, right? You say Pictionary?
Yes.
Okay, which one's going to be the most helpful for you to find maybe a pattern as these extend out? Okay, so maybe think about those tabular representations. So, come grab some cubes to help you build out this relationship. Work with your small group. Get your ideas on the vertical surfaces as we are working through this process. I guess actually, let me ask this. What questions do you have before I release you to start working?
Yeah, bro, I guess we're talking about here those ideas.
Ready, set, go!
That's it.
Thank you.
That was
Thank you.
I mean, no times four.
Thank you. Okay, so if I can grab y'all's attention, let's look at this really quickly, and I need us to make sure we take some pictures and talk, so we're prepared to talk about this a little bit more tomorrow. So if you can walk this way a little bit, I want us to notice something, okay? So when we talked about 3 painted faces, I know this group has a different response, but what did all of y'all say for your 3 painted faces? You said, oh, you changed it? So it's 8. Why is it 8 for the 3 painted faces? That's the what? Those are the corners. And how many corners are we always going to have?
8.
Aren't there 8 corners? So I need us to pay attention to that, right? So 3 painted faces is those corners. Does anyone know what kind of function we would call this when it's always 8?
No.
Oh, that's right. It's constantly 8, or a constant, not factor. It's another F word. Function. Notice, it's literally quite saying y is equal to what? 8. Now I want to talk about the 2 painted. Oh. So, Kelly, can I see this real quick? Thank you. So, everyone noted that there was 0 cubes with 2 painted faces for case 2. But in case 3, all of us got how many here? 12. Now, Kelly, talk to me about how you got this 24. Times it by 2, but why? You talked about way more than that. I know you don't like me calling you out in front of people, but you had some really good ideas. What were you talking about? How did you know to multiply it by 2? So look at all your edges here. There was a 1 in the edge. Now how many are there in this edge? There's 2 there, right? And so each of those edges, those 12 edges, is going to have 2 for a total of 24. Now, I just want to make a prediction. I want you to make a prediction. So we know this constant, that's 8. How many edges are we going to have here? 48, you think so? What do y'all think? So let's remember, if I go to a 5 by 5 by 5, this was 4 right here, right? But if it's 5 by 5, it's going to be 5. And I've got 2 corners. How many are going to be on the edge? How many? 3. So it's going to be 3 wide here. And we're going to have 12 edges with how many? 3 for a total of... So I want us to notice, is this an exponential function right here? Because it sounded like you were thinking we're going to double. Is it exponential here?
No.
What is this? 0, 12, 24, 36, maybe. What is it? What has to be here to be linear? Constant. Is this constant additive here? Constantly adding 12. So we had a constant function which is degree, anyone remember? Not 1, because that was linear, degree 0. Notice there's no variable here, is there?
No.
This is what type of function? Linear, which is degree 1. And so we're going to continue this tomorrow. Because we still need to figure out the 1 painted face, we still need to figure out the 0 painted faces, and I need us to continue to think about what's happening here. So, make sure you take a picture of your work. Your bell ringer will be to get this work back up there. We will do a demonstrate your understanding later in the day. Yes, we'll start back in the same groups. So I should probably take a picture of the groups real quick. Yes, how about this? Put your cubes on my back desk back here, and you can just grab them from the back desk. Take a real quick
We have to.
picture of,
So your other classes don't do this?
my other classes are 2 or 3 weeks behind y'all.
Oh, whoa.
They behind.
This is event.
Yeah, y'all, they complain about how fast I'm going, but
They ain't going that
I would agree. I tried to find a good balance.
Nah.
I would not say I do it perfectly, but I do try to find a good balance.
Oh,
Bella, can you grab that cube down there, please?